slammer like the hip hop song. Wanna keep it slammer like the hip hop song. Keep it slammer like the hip hop song. Wanna keep it slammer like the hip hop song. Keep it slammer like the hip hop song. Like the hip hop song. Like the hip hop song.
So we're ready to go in 5 seconds. Hi everybody, good morning. Okay. Do we have the online speakers?
Yes.
Yeah.
So Enrique is going to be presenting.
Yeah.
It's if the others don't speak, it's okay. Elena is not online, that's not a problem. Alba is online, but it's not mandatory that she will speak.
Right.
Okay? So Enrique is the main guy.
So it's not neither of them don't need to speak. They don't have to.
Yes.
Oh, I understand. Alba's there already, so you decide, because you've got 15 minutes, you decide how you want to. Okay, good morning everybody to day 2 of Escape Conference to the Future. It's quite fitting actually, the venue we're in when you see all these dinosaurs. It just dawned on me today in the title of the conference. So just a couple of things before we start. You all got a goodie bag yesterday, and I don't know if you had a chance to scroll through the Escape Legacy booklet. You probably authored it, most of you, but it's extremely interesting. So do have a browse of that. So we're going to kick off this morning with the Virtual Research Environment, VRE for Escape Science Project, and we have Enrique Garcia from CERN, Alba Vendrell, and also Elena Gazzarini. If I can just introduce Enrique, and then I'll let you start. So Enrique is a fellow at the CERN IT department, working on the EOSC Future and InterTwins European projects. So with the rest of the virtual research environment team, you're implementing an ecosystem of tools and services. So it'd be really interesting to hear how that's come through. Over to you. Thank you, Enrique.
Okay, thank you very much. Perfect. So, hello, good morning, everybody. Thank you for the presentation. I'm Enrique Garcia, and I will be presenting the virtual research environment for the EOSC Future Science Project, of course, on behalf of all these people, Alba, Elena, Agis, Dominic, and Xavier. Okay, so let's get started. I would say that the most important slide of this presentation is this one, to have an idea clear of what is exactly the virtual research environment. So the VRE is no more than a collaborative online platform designed to fulfill the scientific needs of the EOSC Future members, EOSC Future Science Project members. This platform, is basically developed to, in this platform, you are basically able to develop and share analysis and workflows, as well as to access all the digital content related with a scientific result. Of course, all of this in compliance with the FAIR principles. Why this is needed? Basically because we need a single platform in where users can perform these tasks, so basically analyze, run, rerun, share, and preserve, as well as they can use it for learning and outreach purposes. How we have been doing this? During the last year, all the members of the Extreme Universe and Dark Matter Science Project have been actively using this platform to run their analysis and workflows on the research topics, and they will present in a moment. Also, they have been adding their project subjects as well as into this webpage that you can see in a snapshot here as well. And this landing page basically contains also the links to all the services and tools. So let's get a bit more, let's explain a bit more in detail what is exactly the VRE. So a general snapshot of this platform, is the one that you can see here, that is basically composed of 4 main components. So let's say that any user will arrive and will be into a user interface and will be able to find a storage site and a computing site all connected together within an authentication and authorization infrastructure. I will get in a moment a bit more into details into all these components. So from the storage side, the VRE is basically composed of a data lake infrastructure that it is based on the WLSCG model. Basically, it's a Russia instance that connects the different Russia store elements of the different sites, thanks to Russia, FTS, and the Greek technologies. Basically, this data lake infrastructure is taking care of all the data management, and as it has been presented already by the work package 2. Basically, any user can get into this, any user that connects into the virtual research environment, does this, thanks to an authentication authorization infrastructure that the identity is provided via X509 certificates and OIDC tokens. That is the escape IAM. The user interface connects this storage site together with the computing, as we will see in a moment, but basically allows the user to speak easily with all the storage site. So basically, it hides all the complexity of the Russia instance and allows user to basically through a user-friendly interface connect all the data, connect to the data lake. Because this because this user interface is basically deployed using a Kubernetes cluster and basically it's a Jupyter Hub, it allows also bringing some computing environments of some pre-installed software. And these environments are the one that all the users of the VRE are using to run their analysis, their preliminary analysis. Of course, this user interface, it will be later connected into external computer clusters. So there will be no need of making the copy from the storage side into this user interface. Finally, the computing side, thanks to the Jupyter Hub, it is not very big in the moment, but basically allows users to send job submissions allowed users to send jobs to external applications, and also in the close future, this will be connected to heterogeneous resources as cloud resources and its PC clusters. Okay, so again, the VRE what it's doing, it is allowing the connection into a interface in where the storage, the computing, is everything connected. So to give a snapshot of all the technologies that are being used currently, this is just I'm not going to get into details, but basically from the authentication side, we are using the Escape AM. From the storage side, we are using, as we said, the Rusho FTA script and the Rusho instance. And then the user interface is basically connecting a Kubernetes cluster, deploying a Jupyter Hub in a Kubernetes cluster that allowed the user to enter in this analysis platform and use the different computing resources. But for the moment, and also the user is able to use the different escape services that are entering through it. So basically, the future pieces of the VRE will be how we will connect the VRE, the virtual research environment, with the different EOSC resources. So one thing that it has been done already, it is that the VRE has already been connected. Sorry, I mean again, it's 3 buttons. In the storage side with cloud storage from the CESNet Institute. So basically in the Rusho instance, we have already connected EOSC resources provided by EGI. And as well, we have installed a RANA cluster on a Kubernetes cluster at the CNAF resources, also using OpenStack. So basically, what we are doing is in this platform, connecting all the storage, connecting what is currently done with resources from provided by EOSC. As I said, the storage side in the storage side the cloud storage, and in the computing side, RANA has already been installing in a cluster on CNAF. That's I would say that's pretty much a summary of all the technologies that we are using. Very quickly, despite that RANA will be presented a bit later thanks to the postdocs. RANA is a framework that allows reanalyzing results. So basically, it is another cluster that basically allows reproducing and reanalyzing, more than reproducing, reanalyzing, sorry, a result that has already been created, a result that has already been obtained. So wrapping up very quickly, what we are trying to build with the VRE is no more than an analysis platform in the end, in where the data that basically comes from the different escape experiments, it is firstly managed by the storage site. So in this by the Russia instance, in where all the orchestration and management is done, as I mentioned before. Then, in the moment that we connect into in the moment we are in the platform, we can also analyze using preserved source code and different analysis environments, in where we can make use of the different escape out work packets. And once we have obtained a result, these results can be combined and compared inside this platform, and because everything is online and connected thanks to the computing and storage site. And finally, this analysis can be preserved and later compared with other analysis and workflows thanks to different platforms that allow reproduction of workflows and reproduction workflows. Sorry. In this case, we are using Rihanna, but I mean we are as the postdocs will show a bit more in a moment. Okay, so I prefer stopping here and leaving the room for questions if there's any, and then leaving the postdocs of the EOS Future Science Projects, well, postdocs, the members of the EOS Future Science Project present how they are using this analysis platform. Thank you very much.
Thank you, Enrique. Thank you very much. I'm not sure if there are any questions online. No, but we do have a question. Livia at the back. Thank you.
Thank you for the presentation. So maybe I do a little introduction. I'm not part of the ESCAPE project, but I followed the ESCAPE project because I am very interested in all these developments, and I've been invited to some meetings thanks to my expertise. So I'm doing radio astronomy. I'm not doing LOFAR, but So I'm working on NENUFAR, which is attached to LOFAR somehow. The thing is that we are trying to, on my team, do the same as this, but we've not been funded through ESCAPE. So my question is there
Sorry, could you just introduce yourself?
Oh yes, I'm Baptiste Cecconi from the Observatoire de Paris, and on the NENUFAR project, which is an SKA Pathfinder. I am in charge of setting up the data center.
Okay.
So with the data lake and everything. So we started to do this work, and my question was, do you have plans for dissemination of this knowledge and experience that you gained through ESCAPE to the rest of the community? Because in a project you can't put everybody, and that's a fact in a project. You select teams to work with in the first place, but then there is a lot of other teams that are trying to do the same thing, and this expertise paid by the European Union should be disseminated, and not only to provide access to the service, but also to have other teams being able to reuse those technologies in an efficient way.
So thanks a lot for the comment basically. I completely agree, and one thing that it is already being done. It is that there's already a working group created between ESCAPE members to share this knowledge basically. So basically everybody has tried to develop similar infrastructures, especially Russia instances, and how to connect them within a Jupyter Hub, are already in contact in a VRE working group, and anybody from the collaboration and outside it is open. So the idea is to basically keep sharing knowledge between the community, and for sure.
Thank you, Enrique.
Sorry. So to the answering for the European level, we should probably do that, but I don't think if there's any initiative at that level. But yeah, it will be.
Before passing to Giovanni, we have another question here. Can we just remind everyone just to say who you are, where you're from, also for the benefit of those online? Thank you.
All right, this is Raymond Roonk. I'm from SURF in the Netherlands. We are basically a national HPC center, also networking, storage, etc. My question is, we also have an understanding of what VREs mean. So we have clouds where people say, give out VREs to researchers, especially the long tail. And my question here, we mostly focus on getting the software environment right for people. I'm kind of wondering where this is in your VRE. So the SaaS, the software as a service, the entire ecosystem, that they can find it ready to go. Because what I'm seeing here mostly is interfaces, but not actually the community software.
Very good question. So for the moment, the EOS Future members are using their specific software. We will need to think about it, how to include basically the community software into the.
Yeah, so I think things like containerization, the ESSI project, EASY, for example, with deployment over CVMFS might be very useful. Those kind of things you could think about deployment, and might help a lot for the long tail at least.
Yeah. In any case, we need to think how this will be evolved in the future, in the moment that it scales up also. Yeah.
Very quick intervention from Giovanni, and we need to move on to the next session. Thank you.
Just to say to the previous colleague from the Observatoire de Paris, that the VRE was conceived to merging the blocks, as you have seen, of the EOSC cell, escape cell, furthermore hosting the science project, and in the future, but in the next months and starting from next year, we want to deploy and operate the VRE for any kind of open science project. So that's the way through, also in cooperation with EOSC Future, that's the way through which we bring the development and the operation of the VRE at European level. Then we have to cooperate together how to disseminate, but furthermore I will add your contribution in the VRE, because you belong as well in ESCAPE, because ESCAPE is a domain-based, is extremely important in a way that we do not replicate, and we cooperate in hosting all the open science projects from our community.
Okay. Thank you, Giovanni. Thank you very much, Andy. A round of applause, please. Thank you.
Thank you.
Okay, moving swiftly on, I'd like to have our chair of the next session, the Dark Matter Science Project, Caterina Doglioni, professor at Lund University and the University of Manchester, together with her panelists, please, if they could come up, Jared Little, Valerio Ippolito, Axel Gall and Alex Ekman, Pooja Bhattacharjee, Christopher Eckner, Francesca Calore, Lucas Heinrich. Thank you very much. Over to you, Caterina, thanks.
Right? Thank you very much for giving us the chance to speak. We're here, the majority of us are here, a few of us are on Zoom. And we will talk about this Dark Matter Science Project. So I don't know if you're going to pull up our slides. We'll do the introduction one by one when there are the talks. Oh, okay, so this is the slide. I see. Very good. Thank you. So there's a number of people, postdocs, students, seniors, supervisors, and coordinators. I'll introduce them one by one whenever the talks come up. And in the introduction, I'll introduce you to dark matter. It probably does not need an introduction. It's one of the biggest questions we have in particle physics, but in general in physics and in science. What is dark matter? We have a lot of evidence only from astrophysics and gravitational interactions for the moment. So we need to find out what this 85% of the matter in the universe is. And how are we doing it? There's a lot of big experiments, big science experiments for dark matter. And these are cutting-edge experiments, and you can only do a few of these at a time because they're large, complex, costly. So we need to maximize the science output. So creating and storing new analysis, data sets, and results, combining multiple results, reinterpreting existing studies. This is all what we want to do in the Dark Matter Science Project. We want to try and provide the community with the tools to do all these tasks and allow access to data and software. This is going to be done on the EOSC using ESCAPE infrastructure. We're a prototype, so we're not going to be completely inclusive or using all the possible dark matter signals or dark matter hypotheses. We're mostly focusing on one that is quite well known. It's the weakly interacting massive particle. where we can look for these particles in indirect detection. So when we try to break dark matter annihilates and then creates particles that we can see, ordinary matter. There's direct detection, where you have experiments usually on ground, where you shake dark matter because you try to shake your nuclei inside your experiment by a dark matter particle. And then you have collider searches, when you have a known particle collider, and you create dark matter particles. And all these experiments have different data sizes, workflows, and results sharing policies. So this is the challenge here. How do we make all of this work together, not only at the level of the science, but also at the level of the tools? So let's think about a discovery scenario. This is very out there. I'm not promising that dark matter is going to be there, and all of these are sketches, not realistic. But say that direct detection sees a hint of a signal with characteristics that are compatible with this dark matter. Then another experiment confirms these hints. And then you have an indirect detection experiment that observes signals of dark matter annihilation. They kind of match in terms of masses of possible particle. So you build a future collider, say, I want to really investigate that dark matter particle if it's there, same way that the LHC was built for the Higgs. And this is how we could shed light on the interaction between dark matter and ordinary matter. So how does this work? How do we do this? We do require interoperable and reproducible analysis, because we need to compare and combine results. We need to have end-to-end workflows available for cross-checks. So this dark matter science project, we're trying to build a prototype to fulfill these requirements. And so the experiments in dark matter science project, they'll be introduced in the talks. There are DarkSides, Atlas at the Large Hadron Collider, and Fermilab and KM3Net. There's also CTA as an evolution of indirect detection. So we're also trying to understand the computing and analysis challenge for future experiments. What are our science outputs? So we think about domain science outputs, so individual results and publications, plots that highlight the complementarity of the experimental efforts, and also, if we manage, combination of experimental results. We'll also have the data and software objects plus the pipelines. So we want data on the data lake, we want software on the ESCAPE software catalog, and everything tied together, accessible by the VRE. This is a potential analysis workflow, so this is simplified, but this is how we do it. We take data, whether real data or generated data, we process it, we analyze it, and then we interpret it. And so the technical solutions you've seen in Enrique's talk are Jupyter Hub and Rihanna. We can do the analysis there. And the ESCAPE tools that are going to be used are the virtual research environment, the data lake for the data storage side of things, and the software catalog for the software side of things. And this is how the test science project integrates with the infrastructure component from ESCAPE. And I just wanted to conclude this introduction, and possibly, if we can keep the questions for the end, for the general, after you've seen all the talks. And the talks we're changing the order a little with respect to the agenda. So the first talk will be dark matter particle colliders. This will be remote. This is Searches in the Atlas Experiments by Jared Little. Then we have a second talk about direct detection, about DarkSide plans and results. Then we have and this is also remote. Then we have the third talk for indirect detection. This will contain a demo with Fermilab results and CTA plans by Christoph and Pooja. And KM3Net will be covering the Extreme Universe Science Project slot. Then we have a final talk gathering a bit the interest of everyone. What can we do for when we have big data and we want to compress it? So this is an example of a tool that could go beyond just one experiment. This is by Axel Galen and Alex Ekman. So here I just give the remote microphone to Jared on dark matter particle collider searches in the Atlas experiment. So Jared is a postdoc at LAP, and he's supervised by Tanya Hernova and Stefan Jezekel, and I'm also the co-supervisor. So Jared, if you're online, I think I will be switching the slides, so just tell me when I have to do it. Do we have Jared? I think we have a potential problem in the room that we can't hear Zoom.
Jared, maybe turn on your video and you can.
Okay,
gesture. Because I see your.
And so, hello?
Yeah.
Can you hear me?
So we can hear you, and we should see the slides as well. But we're moving the slides from here.
Okay, so you can hear me now?
Yeah, we can.
Okay.
Just wait a second until we put the slides up from our side, and you can tell me when to switch.
Okay, excellent. So yeah, I guess I'll begin. Thank you so much for the introduction. First I want to just introduce the Large Hadron Collider and the ATLAS experiment quickly. So the Large Hadron Collider is the world's largest particle accelerator. It's the final stage of a series of particle accelerators that is 27 kilometers around, and the design center of mass energy for colliding protons is 14 TeV, although this has been stepping up over the years. We're currently running at 13 and 13.6 TeV. The beams inside the LHC, they collide at 4 locations where we have particle detectors located. So ATLAS, CMS, ALICE, and LHCb. So the ATLAS experiment, along with CMS, are the 2 general purpose detectors located along the Large Hadron Collider. And these 2 experiments are independently designed with different technologies, but they both study a wide range of physics. So for example, the Higgs was discovered in 2012. That's observed both by ATLAS and CMS. As well, we perform precision measurements on standard model properties, and a large program is searching for new physics, including particles that make up dark matter. And an important point to mention is that these are designed to be hermetic, so we observe as many possible decays as we can. So next slide. So yeah, in the next presentations, you'll hear about the indirect and direct detection experiments where they search for dark matter signals in or from outer space. But for this presentation at the LHC, we're trying to make dark matter by colliding high energy protons. So in the nice diagram that was shown before, we have the 2 standard model particles going to the right, where we're colliding the 2 protons, something happens, and we end up with dark matter in our final state. But how can we detect this? So next slide, please. If we make it, how do we see it? Dark matter, we're looking for weakly interacting dark matter, which unfortunately would not leave a signal in our detector. But the good news is we expect energy conservation in the transverse plane. And so this will be the main evidence of the presence of something missing. So for each collision, we calculate the total transverse momentum for all of the particles in the detector, so-called MET. So we expect this to be 0 since the protons collide head-on. And if it's not 0, something has escaped, and this can be evidence for invisible particles. So you see in the diagram on the left a head-on view of looking down the beam pipe. So after a collision, you may have in the transverse plane 2 particles like this, and some missing energy in the blue pointing outward. That would be some evidence for some potential particles that escape our detector. Experiments that look in space, we need these to confirm that these invisible particles that we potentially discover are dark matter. At the colliders, we actually probe the interaction between ordinary matter and dark matter. So we search for a new particle that may mediate this interaction between the protons and dark matter particles. So we search for these new particles responsible for this interaction. Next slide. So the current status, first I want to talk about the inclusive dilepton result. So I focus on the dilepton where we have 2 leptons in the final state. And so we see for run 2, we had a dilepton resonance search that looks for potential new particles decaying to 2 leptons. But if we see no signal here, we can put constraints on the fiducial cross section of this new particle, generic Z prime particle. So in the plot on the left, you see a data Monte Carlo plot for the previous in the dielectron state. So we're looking in this for a bump. So it'd be evidence for a new particle that are decaying to these two leptons over the background. So you can see a few in the dashed red lines, hypothetical examples of different particles that we may observe. And the solid red line is a background fit to the standard model backgrounds, and you see the data follows this quite well. So these limits were set on the fiducial cross sections. But this doesn't mean we should stop here and give up. We have large backgrounds in the region below 1 TeV, or the line shown here. Well, some well-motivated dark matter models could, in fact, escape detection in this analysis. So we're looking to improve the sensitivity to new physics by performing a more exclusive, specific search targeting some missing ET, as well as two leptons. So in general, I have two projects within this science project. We'll look for these exclusive models where we expect new results early next year. And as well, I performed a reinterpretation of the inclusive search in terms of dark matter mediators. So looking for these mediators decaying to dark matter using these results. So this has more or less been completed and implemented. So yeah, next slide, please. Which I discuss here. So we use this dilepton search to constrain dark matter mediators. So if we have the Z prime particle with a non-zero coupling to leptons, we would expect to see this produced as an excess in the data. So I'm using these results to set limits on this particle. So in the case you see on the plot on the left, we have the red line, which is the expected limit from this analysis. And we generate new signal models, dark matter signal models, assuming a particular dark matter mass and Z prime mass. And then we generate many of these to compute this fiducial cross section and see where this crosses the limit here. So for this, for example, we set a dark matter and we have to simulate many Z prime samples, as well as, and then afterwards we set these limits and we summarize over the different dark matter masses as well on the right. So you can see it fills 1 point on the summary plot. So it's a sort of a two-step process, this little project. These results are actually extrapolated up to 14 TeV. So the 13 TeV analysis was done already. So for the SNOMAS effort in the US, we wanted to see what we expect at the high Lumi LHC. So we did this as well at 14 TeV with sort of a scaling up limit here, which was included in this report. So I show you here the plot at the right for this. The purple here is the dilepton results that we had. So next slide, please.
So you have about 1 minute left.
Okay, thank you. So just wanted to discuss this analysis I implemented as much as possible in the VRE. So you see at the bottom left, I have a terminal in the data lake as a service. This is where I did much of my study and made the plots that I showed previously. But we also use these to set up a test case with Rihanna, sending the jobs to remote computers with CERN. So in this case, we can set up a multiple stage workflow that we can send and pass the output to the following stage. So I have one job submission that I send, and it runs both stages of this and then pushes it to the remote system. And you can view with the web interface as well the outputs of this. So next slide, please. And so just a few words about the new results that we're also looking to get, the new analysis targeting dilepton resonances in the dilepton plus MET final state. We're searching for 3 well-motivated models that could have escaped detection up to this point. And I link here the paper here. This was developed, this was proposed by theorists. So we use these benchmark models to help guide our techniques, but we aim to stay as general as possible. We want to make these reproducible and reinterpretable results. So we don't want to just focus on these 3 models. But by targeting these events with this final state, we'll be sensitive to low mass regions where the dilepton analysis was dominated by more standard model events. So next slide, please. So this is my final slide. So there's a small reinterpretation project we implemented, and it's almost fully implemented with Escape tools. Interactive Jupyter notebooks were also set up, I forgot to mention. This allows the users to follow the different steps of the analysis. As well, we use this to test the connection with the computing infrastructure with Rihanna. So with samples in the data lake, the workflow can be run on the Rihanna cluster. So in the dial-up-ton analysis, we're looking to have some new results early next year that we can start playing with. And I'm developing this with the EOSC future framework in mind as much as possible to allow for a seamless transition. Thank you.
Thank you very much. So we have time for one question on this talk. And if there's anything on Zoom, I can't see that. Okay, so I think we are ready to move on to the next one. The next talk is about direct detection, and it's Valerio Ippolito. He's a staff researcher at INFN, and he will talk about the dark side plans and results.
Thank you. So if you go on the next slide, what we try to do at DarkSide is to detect the dark matter, which is in the universe already. So you see on the left, we are looking at a different part of that sketch. The idea is that dark matter would hit our detector, which can be seen as a big, large pool of liquid argon. And it would hit a nucleus, which is the thing in blue on the sketch on the right, which then travels in the liquid, and it can lose energy, lose its kinetic energy mainly in two ways. One of them is exciting atoms, so that we can measure the scintillation photons out of them. And the other one is that of ionizing them, in the sense that we can use electric fields to make those electrons drift towards a gas phase in which we are able to measure them again in the form of light. Now, the idea behind all this is that if we manage to reconstruct the kinetic energy of the nucleus, the thing in blue, we can tell something about the dark matter mass if we observe any kind of event. The challenge is that this kind of interaction is quite rare, so we need large detectors which must be free from the contamination from natural radioactivity. So if you go on the next slide, we started doing this within the DarkSide collaboration in the DarkSide 50, effectively, which is an experiment of 50 kilograms of liquid argon, which lasted until 2018, and which basically proved the technology, which is going to be leading for dark matter between 0.1 and a few tele-electron volt, but which also showed, surprisingly, also for us at the beginning, world-class sensitivity to light winds, so light dark matter with a mass of a fraction of giga-electron volt. We are transitioning now towards DarkSide 20K, which is going to be 400 times larger. It's going to be 20-ton detector operating for 10 years, starting from, let's say, 2026, which will then be able to scan in a unique way the TeV scale. Plus, we have additional projects which go beyond and tend to go in the direction of pushing the discovery power for dark matter to its experimental limits. On the next slide, the strategy, which is behind our dark matter search is different for light and for heavy winds, for heavy dark matter. In the case of heavy dark matter, that's the simplest kind of search, in the sense that we do the reconstruction of those two signals I mentioned before. On the left, we picture them as S1 and S2, in the sense that one arrives before the second. And the combination of the two helps us reduce completely, almost to a zero background level, all the radioactivity background from the detector components, from the surroundings of the mountain we are operating our detector in, and so on and so forth. While in the case of light dark matter, then we need to use a lot the help from the Monte Carlo simulation, which makes everything look like the Higgs boson discovery at the LHC, so something like having large data sets from the computing point of view and understanding them from the physics point of view, and so on and so forth. In both cases, what's crucial is to be able to model the response of the argon detector to energies which are very low with respect to the LHC. At the LHC, we talk about energies of the order of GeV, meaning giga-electron volts, to be compared to kilo-electron volts of kinetic energy deposited in the detector. That's a big challenge. And another big challenge is that we will face with the large-scale 20-ton detector, the DarkSide 20K, because there we will have 10,000 silicon photomultiplier based detectors acquiring data, which is going to be huge for these kind of experiments, like petabytes per year, which implies that we need to use complex filtering and machine learning techniques to be able to cope with those data and understand the WIMP and the dark matter signals. So on the next slide,
you have
our analysis
a minute left.
Yes, thanks. Our analysis workflow, which is here shown on in the case of the high mass dark matter search, is quite modular. So what we're doing is to try to integrate it within the EOSC Future TSP. So the idea is that the main assumptions would be behind any interpretation, which are done usually outside or in the final paper of the collaboration, are the signal, how the signal would look like, how our dark matter signal would look like, and how the detector response looks like. So we're trying to put everything which is here in a modular way outside of the dark side only box in order to be able to do that with open data. On the next and last slide, you can see that it is working quite well. On the right, you see the high mass dark matter the dark side 50 dark matter results. The top is the published result. You need to look at the black continuous curve, and the bottom is the open database result, which are now transitioning fully within the VRE, profiting from the fact that we can use the authentication system to exercise in an embargoed mode and to extend all this also to the asset search for dark side 50, which is a low mass dark matter search, plus everything which is related to moving towards the next generation of experiments, so exercising reconstruction techniques for dark side 20K. Thanks a lot.
Thank you very much, Valerio. We also here have time for one question, if anyone is curious. Doesn't look like there's questions now, so we will keep the time at the end for questions on the overall and also on the talks, if anyone wants to ask. So next we switch to speakers in the room. So the next talk is by Christoph Eckner, a postdoc at lab. And okay, so you change this. You can introduce your talk. And then this is the, for both of you. For both of you, you should finish. Like this is your last minute.
Okay, all right. Okay, so right, thanks for the nice introduction, and now let's break dark matter. So, well, if I say we break dark matter, this means that two dark matter particles will pair annihilate to produce standard model particles, and after some processes, you get stable particles that travel through the universe, more or less. So this could be charged composite particles, leptons like electrons, positrons, neutrinos, gamma rays, all of that. But here you probe exactly those processes that were there in the early universe to produce dark matter in the first place. So how do you detect these particles? Well, here we'll only focus on gamma rays, and the rest is just depicted here. Well, for gamma rays, you have multiple options. At high energies, you can use ground-based telescopes, while at low energies, you rather go in space, and there you have Fermi Large. And here we'll focus on. So what can we do? Well, first we have to predict what is the signal that we expect from annihilating dark matter, and typically this is cast in this form, this formula that consists of two parts. In red, you have the particle physics term that encapsulates the model that you inject in order to produce some thermal dark matter, and you can scale the signal with the parameters of that model. And in green, you have the integral over the line of sight of the dark matter density square, which is the so-called J factor, and that determines the strength of your signal. So you would rather look for targets with a very high density. In our Milky Way, that is the galactic center, but there might also be subhalos or satellite galaxies of the Milky Way that are suitable targets, or galaxy clusters for extragalactic sources. Now, if you look at the, If you look in the center of the galaxy, you see in Fermi-Large data that it's extremely crowded with gamma rays, so there's a high contamination by background, and that's a complicated target. While at high latitudes here, the contamination is much less, and you can search for those signals. So here you have a moderate signal from subhalos or satellite galaxies and the low background. And that's what we're going to do. So here you see we have detected some of those subhalos which have some stars in them, so-called dwarf spheroidal galaxies. They are very low in background, they're close to us, so that the suppression by the distance is not that large. And they are, because of that, quite clean laboratories for dark matter annihilation. And Fermilab has used this to set stringent constraints. Now let's go to the Fermilab limits. So what the collaboration does is usually to look in the sky, to select one dwarf spheroidal galaxy, put some region of interest around that, have a model for the astrophysical background, fit that to the data, and then stack multiple targets. Now that has some problems because the model is usually an all-sky model, or at least the emission from the galaxy is all-sky, so different patches fitting them individually might not be that good, and you have some kind of contamination. And your fit might not really encapsulate the real physics, or it's inconsistent, more or less. So what we try to do is to do it in a consistent way and to acknowledge this for the full sky. And this is where our model comes into play. Here you see we select different patches in the sky where you do not have bright sources or dwarf spheroidal galaxies. You collect the data and then you feed it into a machine learning tool that learns how to predict the background at the particular position that you're looking at, plus the uncertainty on this prediction. And so you have some consistent treatment of the astrophysical gamma ray background. And this is then employed in the typical way that also Fermilab analyses use. So you have a stacked log likelihood function that contains the uncertainty on the J factor. That is typically done also for Fermilab, but we have the option to inject some background uncertainty too, and in a consistent way. So that is our benefit here. And you see we can set limits from only a single target and combining them in gray. And we can then compare this to Fermilab limits. And you see, if you do this in a consistent way, considering the background at least, you can kind of decrease or lower the upper limits you see from dwarf spheroidal galaxies, leaving room for example, the galactic center excess of Fermilab. So this is still allowed given this treatment that we employ. And Pooja will now present to you how this pipeline works.
Thank you. So now we have Pooja Bhattacharya. You can come over here if you like. And she's also a postdoc under the supervision of Francesca Calore at lab. So slides are there. Then you should be able to press.
Okay. Hi, hello. My talk will be actually the continuation of the Christopher's talk. Christopher has already told you that how the Fermi dwarf code will work and what we can obtain from that code. But the purpose of my presentation is that to implement this code to the VRD platform and try to see whether we can get the same result from the VRD platform. Besides, we also would like to check whether we can also use the Ruscio, as a data lake, and can run our code. So before proceeding to the further details, I first want to give you some details like what is the structure of this code and what is the domain of this code. So it is, first thing I want to say, like if you check the data province, this code is actually derived on the Fermilab data. Fermilab is a gamma ray space telescope, and the good thing is that the data obtained from the data detected by the Fermilab is publicly accessible, so anyone can go and anyone can use and anyone can run that data. And another thing is that the programming language of this code is Python 3. So this is one of the most used language you could say. So anyone can give a try and try to check whether to run this code. And this code is actually derived from the reproduction of this paper, Alvarez et al. This code is already available on the ESCAPE OSSR, but right now from the VRD GitLab you can also find that code. And from this VRD GitLab you can also find the Python, and also the Jupyter notebook will be also there, and the manual will be there. So you can also go and give it a try, and all the details will be there. I mean, all the things to reproduce the result will be there. And, and for our cases, we also uploaded the data, like in order to run the Fermi-Lat analysis, we need the spacecraft file, we need the photon files, and also other background files, IRFs, and everything is already uploaded to Ruscio. And after setting up the Ruscio data lake and VRD platform, we have run our analysis and can see that, yes, we can perform our analysis and we can call our data from the Ruscio and run our analysis on the VRD platform. So these are the results that we have obtained from our VRD platform. So it also shows that, okay, yeah, we can, I mean, Ruscio is working and VRD platform is very working, and it also works as a very complete work platform. So here I give a flowchart of our analysis. Here you can see which part of data is stored to the Ruscio and which part of analysis we have performed over the VRD. So right now I will come to the outlook of this presentation. Like from our analysis, we have checked that, okay, we can, with using the publicly accessible code, which are designed for the indirect detection and which use the data from the Fermi-Lat, we can derive a completely working platform. And in future, we have few, I mean, there are few perspectives in future, like we are planning to update this code to give the user a more hold on this code, so that user can use their choice of data, choice of background, everything. And yeah, apart from the Fermi-Lat, we also try to check our VRD platform for the CTA data. You know that CTA data is not public, but still Gamma Pi is public. So with Gamma Pi, we can try to obtain the realistic, I mean the sensitivity studies. So, sorry. Oh, sorry. So right now I will give a demo. I think, yeah, okay. So it will be better that way. Yeah, in this demo I will show you like how can you perform the analysis over the VRD. First step is to log into this ESCAPE website, and after login, this is the VRD this is my VRD environment, and here we can see the Jupyter notebook that we have used for our analysis. This is the notebook, and now we'll go to the Ruscio and try to upload the data from there and try to call the data from there. So my data is stored over there, so I just recall that from. You can see all types of, I mean, the most updated spacecraft or photon files or all other necessary files are over there. So for the demonstration, we'll just call few files, like you can see I just call few files and rename it. Yes, like that way I'm just trying to add it to the notebook and give it a name. From the notebook, you can see that there are 3 files that I have called from the Ruscio. And now I will use that data directly from the Ruscio. In the Jupyter notebook, I will mention about this file. So first I will restart and start the analysis from the beginning. Yes. Yeah, you can see that I will replace the name with the name that I just mentioned when I am calling the data from the Ruscio. And here you can also see the location of the data. You can see it is from the data lake. And there are some intermittent process over there. I mean, this is the process of, like, how can we obtain the cross section for one particular dwarf galaxy? I don't go in details, but if you check that, check our code, you can see like what is the meaning of this part and what we can obtain. I'll just finish this demo when we get the result, so it will be shown. Yeah. Yeah, so you can see that we can obtain the result from the VRE platform by calling the data from the ratio. So it gives that idea that VRE is very much working, and we can use our publicly accessible code over there. And our next step will be to use another program, as I would say, to extend our program for the CTA data. I mean, to use the gamma pi. So yeah, that is it. Thank you.
Thanks a lot, Christoph and Pusha, for the very nice demonstration that really we do have pipelines working on the VRE. So are there any questions, including, I don't know, experience, technical, anything that you'd like to ask? I can't, there's too much light. There might be, yeah, okay, good.
Thank you. You don't want me to catch the microphone, or actually not catch it. Jan Grange, Astron, you know, talking about overly technical questions, I was curious, what are the properties of the data? Are these like many small files, few big files?
Not that big. I mean, it is within. If you consider all the weekly spacecraft and photons file, it should be under 10 or 12 GB. So it is not that big right now. I mean, not in the DAV.
Yeah. So I mean, you know, your workflow is let's download all the data and do processing. You know, if you have a manageable amount of data, that's fine. But I was curious whether you were thinking about, you know, whenever scaling up to huge amounts, whether that would give you a problem if you go to newer instruments or something.
Now, okay. So Jan, yes, there is a good question. So let me probably add a bit of a picture here. So this VRE environment is something that has the capability also to wrap up the analysis framework. In the VRE, you have the software, you have the links to the code, you have the links to the data. Imagine you have a way to wrap up, which is Rihanna, and then send this ball, this star, to computing resources. It could be the batch, could be clouds, could be HPC. So contains all the links to the software, the data, and the code. So this can run on external resources. This means that the data is not local. You don't load whatever their job runs. This is the way to scale. The way that the VRE is presented here is really kind of a prototype. So you run on a small chunk of data, and to scale it up there, you need a wrapper to really be able to export this and use this analysis in a distributed computing fashion.
Just to clarify, is this totally open in the sense another user can access with this ID in the IAM of ESCAPE, could run exactly the same analysis as Pooja? Is supposed to be the case. Is it yet the case, or we are not ready for that? And then the second question related to this first one is that the VRE, the functionalities are fine and the demo are really clear. On top of the mechanics, it is mandatory to have a sort of entry landing page where I see Christopher and Pooja work, acknowledge their name, their work, and then links through the VRE to reproduce their analysis, and eventually tutorials and the way that I can interact as a scientist with you both and proposing further analysis for further scientific results on top of yours. Can you comment on that?
So I can, Pooja can say, but this is open, right? This is something that anyone
Yeah,
can do.
the code is open, but if you want, in order to run from the VRE, I think you need the token, you need that
Yeah, yeah.
credential
As long as you
to
can get in.
access that one. Yeah, code is
Yeah.
publicly open, you can run, but I think you need some credential or some things to run over the VRE. If you have, so I think anyone can run, and anyone can call the data from where, because I can access anyone data from the Russia if I have, I can check and can call.
And what about
So
tutorials and landing?
For the second part, it's a part of our consolidation plan.
Okay.
So maybe we talk about it at the end. I have one slide about that. There's not much, but we want to do it. We will do it. Yes.
Thank you, fantastic.
All right, so for the next talk, I'll stay here. We have a machine learning tool for data compression from a PhD student and a master student from Lund University, Alex Ekman and Axel Gallen. So I'll give the microphone to them.
Is the green button forward? Excellent. Right, so let's get started. In vastly different fields of science and industry, I think we all know that we have a problem with too much data and too little storage, right? So there's a high demand for compression techniques and compression of this data, but conventional lossless compression methods, they don't really compress enough. So one solution is looking at lossy compression, where some of the data is lost in the compression itself. The catch here is that to have a good lossy compression of your data, it needs to be tailored to your data. I cannot compress my particle physics data into an MP3 audio format. That just doesn't work. It's not made for that data type. So one solution that we're working on is a lossy machine learning based compression, which is based on an autoencoder. So the autoencoder, it's trained to, oh, that's not the laser button. Can I go back? Oh, there we go. So it's trained to optimally compress and decompress your data. And in the center, called the latent space, you have the minimum number of dimensions, which is where you can save your compressed data. So Axel will now present our preliminary results on particle physics data.
All right, thank you, Alex. So, in order to do lossy compression, we have to pay a price. The decompressed data will not be equal to the actual input data due to the nature of the actual autoencoder. So this must then mean that this is a bad method. This can be quite easily said, but this method actually works quite well in cases where the amount of data that you analyze actually matters. And this is the, this is certainly the case in particle physics, where the more data you have will compensate for the loss which the compression method leaves you with. And one of the current analysis prototypes are actually or are available on the VRE right now, and that is. And now I'm going to show you a quick slide showing the actual notebook, which have shown or made by a Google Summer of Code student called Maxim Namchik, and. Based on his studies, which is on simple particle physics data, for a 38% compression rate, the actual loss from the compression method is only about 0.5%. So this is quite good. And now Alex is gonna just give a quick outlook.
Thank you. So the future outlook for this project is that we have very successful preliminary results for particle physics, and we've started talking with colleagues. We've talked a lot with you during this conference, and we've started to realize that there is a really, really high demand for these type of tools. So the future outlook, our future plan is to create a user-friendly tool on the virtual research environment, but for this to be possible, users of this tool, which is you and our colleagues and people from other fields, they need access to the code to tailor it to their data. They need a way to host their data, and they need the computational resources to train the data set or train the autoencoder. So this is where shared resources like the virtual research environment is absolutely crucial. Thank you.
Thank you very much. We have time for one quick question, and then we conclude with the wrap-up. There's one from Giovanni there.
I think, once again, the landing page for acknowledgement and to provide the tutorials and the virtual discussion with other scientists is extremely relevant in this case, because we have other examples of compression. And now I remember that we also developed one algorithm about which we also published during the precursor cluster Asterix, and inspired by the compression of the images of the Cherenkov telescope. Now, and I think it is in the catalog, because it was in the catalog of Obelix Asterix. So therefore, you see immediately that apart the fundamental approach of having the VRE to reproduce your analysis, with the landing page, I can see your libraries, but I can also talk to you, propose what I'm doing, and team up to make next steps. It's fundamental to bring the two things, sort of a social network, scientific social network, plus the VRE to reproduce the results.
Thanks a lot. That's, I think that's very nice. And it's part of the consolidator. We might even have already the tools to do that on the landing page, thanks to Trust IT on a different projects. We're going to get it done quite quicker than we think. All right, so finally, I just wanted to present consolidation and open challenges. I have about a minute and a half to do this, so I'm going to run through this, and hopefully you won't mind keeping 1 minute off your coffee break if you have any more questions, but if not, you can ask questions at the coffee break. So I'm only one of the 3 coordinators. I've not introduced the others. One is Francesca Calore. She's a scientist at Lab, and she's online, and there's also Lukas Heinrich, who's a professor at Technical University Munich. So I will skip this slide because we know that we're going to prove what kind of outputs we're going to provide. I just wanted to talk about one of the questions that was there earlier is that what kind of disseminations have you done? So we've done some dissemination so far. We've done talks proceedings. We're engaged by a consortia, so the European consortia for accelerators, so mostly collider, particle and astroparticle physics, and nuclear physics. So this is called IENAS, and this is dark matter is one of the topic challenges for the community, so we're engaging with that. We're engaging with communities that deal with fair data for machine learning and also high energy physics. And we have given quite a lot of input to the prioritization for particle physics, the input to prioritization of particle physics in the US, that's called the SNOMAS process. So a lot of what you've seen has ended up being part of white papers, a lot of the scientific results. And in the long-term future, we do want to participate to more conferences, but also we have a wish list of dockathons, citizen science events, how to learn from the dark matter science project experience. And this is something we can do also together with the other science project. So this is we are having impact towards the European strategy update goals. I'll let you read this if you've not read it already. We promote synergies between different communities. This is one of the white papers for the SNOMAS 2021-2022 process. A lot of dark matter experiments are going towards having a lot of data. So this is a question that came there. How do we deal with a lot of data in different formats? Maybe it's big chunks, maybe it's small chunks. So we want to work with the scientific software communities. For example, there's the HEP software foundations, but there's probably more, to define what kind of computing resources we need for future discoveries. And then finally, this is the challenges and consolidations for the dark matter science project. The onboarding of the new analysis that we're planning require very large amount of data, so we're talking about terabytes, so we will have to turn to pledged resources. So we'll really stress test the VRE and the EOSC cell using Rihanna, using more complex workflows. We need to also guarantee restricted data access until the embargoes are lifted, so we will use authentication. We'll publish the software and pipelines on the OSSR. If we have time and then people will use the Gambit software to combine results. And also this is something a bit out there, but it could be interesting also to other clusters, is to expand use cases to real-time analysis on constrained infrastructure. So how can we have different compute resources on the other side of the VRE to emulate situations in which, for example, we can't have all the computing we want. And in terms of consolidations, we want to widen participation of scientists, to use dissemination, training and documentation. have a lasting infrastructure and consolidation work, so we need to integrate our services with the US core through ESCAPE, and then strengthen cooperation and sharing experience across the science projects. So this is the conclusion. I'll let you read them, but I also wanted to thank not only the early stage researchers, supervisors, and funders for all the work to make this possible, but also all the ESCAPE project, because we came somehow at the end and we found a lot of really great work done. So thanks to all of you for making this possible. Thanks a lot.
Thanks, Caterina. Thank you for our online panelists as well. We're now going into the break. Just one point maybe, Caterina, from what you mentioned on the slide before. You don't need to go on to it, though. The consolidation between the dark matter and the extreme universe test science project. So that will be interesting, actually, to hear, because that's coming up next now. And I hadn't appreciated that the two are working together. So that's good to know. All right, a break's on now. We need to be quick, though, so please grab your coffee, and if we can be back in 10 minutes, that would be wonderful. Thank you very much.
Come and ask us questions. We're around there.
Okay, so we're ready to start back. Thank you. Slightly late, but that's okay. Eleanor's a superwoman who can get this on the ground, and she's already ready. So, as we said before, we have a second a second test science project presentation. I get the name, excuse me. The Extreme Universe Science Project. Eleanor Cuoco, she is the head of data science office at EGO, the European Gravitational Observatory, since March 2018, and is also an associate faculty at the Scuola Normale Superiore in Pisa. Over to you, Eleanor. Thank you very much.
Thank you very much, Silvana. So, I'm going now to present the work that we did with all these people listed here, with the postdoc and the supervisor in the Extreme Universe project. So let me start from the starting of the gravitational wave astronomy with the detection of the first gravitational event in 2015. This opened a new way to investigate the universe. We have access to information otherwise impossible to get only through light. Since then, we detected more than 90 events. Most of them are black hole merger. But in 2017, we detected the first multi-messenger event. Two neutron star merger produced gravitational waves, but also gamma ray bursts, electromagnetic counterpart, radio counterpart. And we have the access to an incredible set of information, otherwise impossible for us to get. And we hope to get more and more of these events with the next runs and with the next detector. What do we want to do with inside the Extreme Universe project? The field is so broad, so large that it is impossible to follow the same concept in all the test science project developed inside this big one. But the main idea is that we want to show that scientists working in astrophysics, in gravitational wave astronomy, multi-messenger astronomy, can take advantage of the use of this common tool developed inside ESCAPE and further developed inside the EOSC future. So we take advantage of using this common environment, the virtual research environment, the data lake, and we wanted to build also on top of this common tool also innovative solution based maybe on artificial intelligence or other cutting-edge technique. So we try to identify which can be the physics that we want to investigate with this test pilot project. So we identify these three main areas that concern the extreme universe. So the high energy astrophysics, where we inserted the gamma ray bursts, the active galactic nuclei, and so on. So the compact object linked to the pulsar, to the fast radio burst, and also tackle a concept of fundamental physics, more linked to the gravitational waves, dark matter, general relativity. Each of these field can be investigated through different messengers. So we received from the universe signal in different format with a different information. So we need also to be ready to work with this different information and different data format, from time domain data to image to tracks for a neutrino experiment. In the very next, not far, sorry, future, many of new detector or advanced detector will be operative, and we will receive a lot of this data. And setting now the collaboration among these big facilities is important for the kind of physics that we can afford in the future. So we decided to use the extreme universe to set up this transversal activity among different ESFRI, different research institutes, with the same goal, working on the physics of the data that we can receive through the common tools useful for all of us. To do this, we decided to have not only a single science project, but a series of pilot projects that are linked to the different goal inside the different experiment, and some of these are also mixed. So these are the presentations that now will follow from the postdoc in presence, the one that are in the rectangular area. And the others are other postdoc working on this pilot project that cannot be present. And we will have also one remote presentation. So you can see that we have a variety of postdoc hired in different labs and working also on different and also very theoretical projects. So let me go only fast through the slide of the people that cannot be in person. So this is a work done and developed by Anirban Hein, supervised by Giancarlo Cella at the University of Pisa. Their idea is to set up a test bed to see if we are able to detect the signature of the gravitational stochastic background induced by the lensing effects. So very theoretical, basic, fundamental work linked to the gravitational waves, but they are developing software to do the simulation with the idea of inserting this in the VRE. Another project is from Estelle Pons, supervised by David Sanchez at LAP, and she's working on the fitting of the spectral energy distribution for a blazar. So here you can see the advantage of the multi-messenger, multi-wavelength approach to the data. So the idea is to receive data from different detectors, different wavelength to reproduce information from a single object. And on the same way, also the work done by Sheridan Lloyd from University of Amsterdam that just joined our team, and he will work on the machine learning approach also to fit the emission from active galactic nuclei, and is supervised by Sarah Merkov. And so you can see the variety of the project is very large, and we can show in our test science project that we have the same problems, and we can have a similar solution to tackle this kind of problem. I think that now we can move to the presentation from the postdoc. I prefer to leave the question to the end of the session, so I let the postdoc talk in one after the other, and then at the end, if you have a question, please write down and we will answer after. So the next speaker is Alberto Yes from Scuola Normale Superiore. He's a postdoc working with me and in a team working on Wayfire. So please.
Okay, thank you for the introduction, Elena. Very insightful. And I will proceed presenting the work done in collaboration with Elena herself and a very varied team which includes computer scientists, astrophysicists. So to develop this framework for multi-messenger astronomy and astrophysics, which takes the name of Wayfire. You've heard this word a lot in this meeting, multi-messenger. Basically, we refer to the study of catastrophic events in the universe, which emit large amounts of energy, in different observational channels. This can be, for instance, two main examples, neutron star mergers, such as GW170817, with the naming of gravitational wave astronomers as myself, or in the future, maybe even core collapse supernova. These signals are emitted in different channels, such as gravitational waves or electromagnetic channels, but even neutrinos. The idea was to develop a real-time analysis, which is scalable to big data, since we're in the realm of modern astronomy, where data is in very large amounts, as we heard in previous presentations, and to provide a portable framework, which can be run on any machine and platform. We want to achieve, as an example, transient classification of the events, but we can even think about doing parameter estimation or other very interesting stuff from a theoretical point of view. This is a collaboration done in collaboration with Trust IT Services, and following the fair data principles, obviously, and it's one of the best test cases for me because we're taking data from different types of observatories and different formats, so it's a pretty complex problem even from a computational point of view. We want to follow the best practices for software management, obviously, and you will see this in later slides. Here I provide a complex, fancy schema of the first implementation of Wayfire, and without going through the individual parts, each individual part, the idea is that Wayfire is meant to be structured in Python modules, which each of them has its own GitLab project repository and its own Docker image. Therefore, you can basically set up the entire framework with a simple Docker compose, and this allows for portability. As I mentioned, we want to follow the best practices for software management, so we have a website with documentation, GitLab repositories for the project, for each module, Docker images, and as an auto entry. A first test case of Wayfire, which has been done last year, was to attach it to the ESCAPE data lake. So we took data, let's go back. Data from, open data from the Gravitational Wave Open Science Center from the previous science run of LIGO and Virgo. And we streamed this data through Rusho and sent it to the Wayfire environment, which uses Kafka as an event streaming platform. And it was a gravitational wave-specific implementation, so using our own tools for the analysis of the gravitational wave signals, which were sent in the Kafka stream. And this was done in collaboration with KNAF, where the entire framework was set up in a Kubernetes cluster. As a first test, the actual output were triggers, which characterize the signals, which can be noise bursts or astrophysical signals, and a Grafana dashboard to visualize the actual results, so the information about the triggers. And the future test case, like the goal, the mission, is to get data from all types of observatories, so not only gravitational waves, but also from neutrino and GRB, and obviously this is a complex thing because of the need of memorandum of understanding to have shared data and everything. So as a first test case, we were run on simulations with approval, obviously, of the different collaborations. And the idea is to use gravitational wave, neutrino, and GRB data, and from different science communities, from Virgo, CTA, KM3net, and this data will have different formats. So gravitational wave frame files for our community, but then FITS files, for instance, for gamma rays and neutrinos. And we will be able then to attach our own Docker image with our own analysis, which can be gravitational wave related, but it can be from another collaboration, neutrino or GRB related analysis. And to provide finally even the possibility to use a machine learning analysis which merges the information from all the messengers, in alternative to a single messenger analysis. So I think with this informative slide, I will conclude. I just want to underline the fact that we are in the process of updating the landing page on the VRE, and that we managed to upload data to the through Rusho to the VRE environment, so it's accessible in the Jupyter Hub, which was previously shown by Pusha. And that's all from my side.
Thank you, Alberto. So if you have a question, you can ask after. So I don't know, I'm very scared by the timing. So I will move to the next speaker. That will be online, a remote speaker, Alessandro Parisi. He started with the mean Scuola Normale Superiore, now he's moved to University of Amsterdam with Gianfranco Bertone. This is a clear example of a collaboration. We started this collaboration through the EOSC Future program to share our competence, our skill on a common project. Alessandro? Is connected, Alessandro? Yes, okay. So we will wait. I can move your slide, so it will be easier. You just have to say me when. So, can we at least his audio?
I'm sorry.
Okay, so I see
okay.
Alessandro and the slide. Perfect. Okay,
Uh,
Alessandro, please, the floor is yours.
Thanks for this opportunity. My name is Alessandro Parisi. I'm a postdoc at Scuola Normale and the University of Amsterdam. In this project, we proved to study the dark matter environment of black hole binary with gravitational wave in collaboration to the Scuola Normale and the group of coordinated by Elena Cuoco and the Grappa Institute in Amsterdam, coordinated by Gianfranco Bertone. Okay, next slide, please. Okay, if we a large number of cosmological astrophysical observation predict the existence of dark matter. In this project, we assume the dark matter exists around a black hole, small black hole or supermassive black hole, but in particular, we consider the central black hole of 1 solar mass and the small black hole in the range of 10⁻², 10⁻⁴ solar mass, and then we assume we have a primordial black hole. This is very important because there are no news for concrete existence of a primordial black hole. And clearly, we assume that the spike exists around the black hole, but we can observe the spike as a point source of gamma ray burst and neutrino. And obviously, the structure of the spike depends on the history of formation of black hole. And in some sense, in this project, we fix the value of the spike and gamma. Is fixed parameter in the model. Okay, next slide, please. Concretely, if the object move in the dark matter produces a dynamical friction. The dynamical friction is originally studied by Chandrasekhar in the Newtonian context, and we neglect the relativistic and post-Newtonian correction. And we can integrate the orbital evolution of the object in the vacuum in the presence of the dark matter. And we have two fundamental contributions, the contribution of emission of gravitational wave and the contribution of the dark matter friction. And in these two cases, and we integrate and extract the gravitational wave form in these two scenery, dark matter in presence of dark matter and in the vacuum. Okay, next slide, please. Okay, concretely, the code is available in GitLab and produce the waveform for different mass and different luminosity distance. We study the number of the friction, the number of the cycle we integrate in fundamentally is the difference of the integral of frequency in the vacuum in the dark matter is a fundamental it's very important because we can observe the dark matter is connected to this parameter. In the plot, we observe the two waveform in the case yellow, the blue line represent the two cases of dark matter and the vacuum. The code used to generate the waveform, include the noise, and the whiting will be integrated in the VRE environment probably next month. And next slide, please, Elena. Okay, we can observe in the plot the typically waveform and the noise. typically the noise is very large with respect to the strain, and then in principle, if we know the form of the strain, we can, and we include the noise, we can apply the whiting is fundamentally is a filter for extract more realistic waveform. And this code is public, and we think to include in the VRE next month. Okay, next slide, please. Okay, thanks. This effect is very important because we can observe the dephasing of gravitational wave produced by dark matter in the next generation interferometer, Einstein telescope. And this is very important because the Einstein telescope, if the Einstein telescope observe this effect on the gravitational wave, we have more information by the nature of the dark matter and then yes, the nature of the dark matter. Okay, next slide, please. At the state of the art, we have developed a catalog of waveform for different luminosity distance and different mass. At the moment, we are fixed some different distance in the halo of the galaxy until 6 kiloparsec, and we use the luminosity distance at 100 kiloparsec as a test. For the max, we fix the essential mass, 1 solar mass, and MHU in the range of 10-2, 10-4. And we generate the antenna, we use the antenna sensibility, antenna pattern, and we fix 100 different sky position. Is fundamentally because the waveform, the duration of the waveform is 1 year, and we change the binary in the space and the interferometry in the time. In totally, we have 11,400 gravitational waveform for the vacuum and for the dark matter, and plus some other 800 waveform for test the code, the machine learning code. Okay, next slide, please. Quindi concretely, we use the architecture is based on the convolution deep learning network. The code of machine learning code concretely optimize the feature of the image and the catalog the two spectrogram in the vacuum and the dark matter section. The code is in progress, but probably we finish in the next 2 months. Okay, next slide.
Okay.
Yes, I finished.
Okay. Thank you, Alessandro. Okay, we are in perfect time. So next speaker is Mikhail Smirnov from ChemistryNet. So please.
I see. This is slide. I see. Yeah. Okay. Hello for everyone, and I'm from ChemistryNet, and I would like to present ChemistryNet instrument response. ChemistryNet instrument response function for point source analysis. Okay, what is my motivation? First, I want to adopt the most common problem of neutrino astrophysics for open science. The next is provide an effective tool which can extract instrument response function information from ChemistryNet simulation data. It should have several properties like flexibility in operation and user-defined IRF interface. It should be compatible with other astrophysical analysis like CTA, which is based on gamma pi, and as you know, gamma pi is open source software and it's quite advanced right now, so it's better to follow gamma pi. It should have easy installation procedure, better to use like a pip install or something like that. And the last one, it should have different options for output, like feeds files, histograms tables, and all of them should follow like GIDF format. Here is the layout of Chem3net detector. So Chem3net stands for cubic kilometer neutrino telescope.
It locates in Mediterranean Sea, and it consists of two parts. One part is for low energy neutrino, for low energy oscillation neutrino physics. It calls ORCA. Oops. No. Yeah, the red one, right? Yeah, good. Yeah, this is ORCA. And another one for high energy astrophysics, neutrino astrophysics, it calls ARCA. I'm not planning to go into details how it's built, so basically it has like a digital unit, and each digital unit has digital optical model, and each digital optical model has 31 3-inch PMTs, and all more detailed information is listed here. And on yesterday there was also one talk about KM3net, and basically it's not necessary to repeat one more time. So actually, what is IRF in KM3net? So here you can see a very nice picture that we have like a data. This is like a person, and in the mirror we can see that self-reflection of this person. This is our response. So mirror in this case is a tool which can be associated with instrument response function. So going back to physical things, IRF is a property of neutrino telescope. It contains information about the physical characteristics of the detector, such as angular resolution, energy resolution, effective area or effective volume of the detector. What's wrong? It allows to quickly estimate the background, and as I mentioned it before, it should be based on gamma pi for cross-experiment use. I think you don't know, but in gamma pi, the IRF determine it as 4 parts. First is effective area, the second one is energy dispersion, then point spread function, and the last one is background. Here, I would like to show you that the most common problem is scientific analysis of distant source. As you can see on this figure, it's quite typical picture of multi-messenger neutrino astronomy. So very far away from the Earth, we have like whether dark matter or extreme universe event, and it produces different type of signals. And usually our goal is to estimate sensitivity, discovery, or set upper limit. And this source usually can be split in different kinds of, like, it can be point-like source here, diffuse source, or extended source. All these sources should follow like a so-called power law. And such analysis was done inside KM3net collaboration. I mean, example of sensitivity analysis is demonstrated on this plot. And now I'm going to the most important part of this talk, is integration with ESCAPE services. It is quite similar what Apuja presented a couple of talks before. Here I'm showing the example of IRF production from DST data files. So DST data files is kind of compressed Monte Carlo simulations from KM3net tools. So first we are going to VRE platform and opening this environment in Jupyter Hub. Then here you can see my notebook. The next step, we need to attach some files from the Rusho. Then we are going to Rusho scope, this one. Here are DST files, and we attach these files to the notebook and rename them. After that, we can run the notebook, and as you can see, there are several new files appeared. So these are our test files, and using our defined KM3 IRF package, which is available in PyP, we can merge these test files to combined IRF.feeds. So after that, we can evaluate what is inside these combined IRF.feeds. For instance, we can open background file and see some content. Already we are using GammaPy functionality, so all these functions are written in GammaPy. And also we can see the content. It's exactly repeats what is necessary to present in GammaPy. It has 4 parts. And it should be stressed that it is reproducible. Oops. It is reproducible and reusable. So thanks. That's all.
So we will go on with the next speaker. It is Dani from Astron. And we will show also a demo for the insertion in a VRE.
Hi, everyone. Thank you for having me, and I hope everyone's having a pleasant meeting so far. So I've been asked to present a demo on one of the test science projects. And so I'm going to show a search for fast radio bursts, persistent radio source counterparts in dwarf galaxies using LOFAR. So that's quite a mouthful, but I'm going to briefly show what this means, and then I'll up on with a demo. No, sorry. The green one is there. Okay. So I have some text, but I'll move some images because an image is worth 1,000 words. And so this search is mainly motivated by fast radio bursts. So these are this is a phenomenon that was first discovered in 2007 in archival data. It is a pulse of radio wave that's coming to us from outside of our galaxy. Here we can see a dispersed pulse. So the pulse arrives first at high frequencies and then later on at lower frequencies at our telescope. And the difference between this and a similar signal from radio pulsars within our galaxies, that this is much more dispersed than what is seen for radio pulsars. So radio pulsars would be found in the green box at the very left of this plot. But as you can see, it goes way, way beyond that. And so we can see that this pulse is going through a lot more medium compared to radio pulsars. And therefore, they are interesting sources to probe the medium between us and these other galaxies, for example. And to date, it's still quite mysterious what emits these signals. It is thought to be related to neutron stars, but it's still an open question. And so in 2016, so quite a few years after 2006, the first repeating fast radio burst was found with the Arecibo telescope in the US. So at first, for a long time, these signals were sort of seen as one pulse, and then they disappeared, and we never heard of them before or afterwards. And then in 2016, this source was found to repeat. So then it was possible to then localize this source to a host galaxy. And so we can see in the blue box an optical image of that galaxy. So it was a dwarf galaxy. And this source was found to be localized in a star-forming region within this galaxy. And not only was there fast radio bursts, so flashes of radio light coming from this source, but also there was this persistent radio source that was discovered that was co-localized at the same place. And so you also had this sort of constant radio emission. And so this sort of gave arguments for the neutron star argument, where you might have a pulsar wind nebula. So pulsars are a special flavor of neutron stars, where you would have a wind of energy being emitted near the star. And so this might be the persistent source that we see. And meanwhile, there's also an interest for search for intermediate mass black holes in dwarf galaxies. So it was hypothesized that these low mass galaxies, so about 10 to the 9 solar masses, might host black holes, but this is quite elusive still. So there are searches that have been looking for compact radio sources in these galaxies, and there have been candidates that have been found. So for example, here at the far right, there are a few galaxies that have been matched to compact radio sources. Some of them are localized at the center of these galaxies, and some are slightly offset from the center, which is different from supermassive black holes that tend to be at the center of galaxies. And it was shown that these two phenomenon share very similar properties. So the PRS and the intermediate mass black holes have very similar properties. So we might actually be looking at the same kind of phenomenon. And last year, there was a second fast radio burst that was localized to a dwarf galaxy. It also is co-localized with a persistent radio source. And as opposed to most of the other localized fast radio bursts that are found in various galaxy types, these two share very similar properties. And so we might be looking at young neutron stars that are in an interesting phase of their life cycle. And so we only know 2 sources so far, so we're interested in finding more in large radio catalogs. And so that's what this search is about. So here, for this demo, I'm going to look at radio sources from the LUTS survey that was presented yesterday, which is a low-FAR survey. It's the deepest survey in radio so far. And we're going to match that to an optical catalog called the Census of the Local Universe, where we can find dwarf galaxies. And we're going to do this search using Matchmaker, which is a Python package that we've been developing. It's in Python. And the details are not too important here, but that's practical to run on the VRE. And then we're going to look at how we're going to use Rusho. We're going to do some cross-matching. We're going to select our compact candidates, and then look if we can find more information in the VO to characterize these sources. And so here, I'm first loading the data sets from the data lake. So they are in Rusho. They're made available. So now we can just link those files in our code. So here, for example, I'm just showing where this file lives in the data lake. So all of this is within the VRE. We're going to load these files later on once we instantiate our classes. We can start a notebook. This takes a second. Okay, so now we can just load a few packages that will be useful, such as Matchmaker, AstroPy, AstroQuery to query the VO, the virtual observatory, that is. Once we do that, we can load our data sets in memory. So for example, I'm going to load the full LUTS, the data release 2, into memory. Once this is done, because this is a Jupyter notebook, we can have access to our data, so we can look at what's inside. So for example, here we're going to see the data. So this is our data set, so this is a large table, essentially. We're going to load the Census of the Local Universe, which is similar. So this is another tabular data set. Once we have those in memory, we can do the cross-matching. So we look at whether these two, well, any 2 sources are falling on top of each other, essentially. Once we've got that, we get indices in both catalogs that tells one line in one catalog is related to another line in another catalog. And then once we've got that, then we can do further analysis. So for example, now that we have the galaxies from the optical survey, we know the distance. We have some flux from the radio survey, so now we can evaluate the luminosity of this source. We can then look for over-luminous sources. So here we've just done some filtering for some sources that are over some relation based on the luminosity and the star formation that is expected from star formation. Essentially, we're looking for characteristics that are similar to the PRSs. We can filter out any obvious black holes using infrared information from the WISE survey, for example. That's another survey within the data, within the VO, sorry. We can check whether the photometric redshift from the Census of the Local Universe matches that from any other more precise redshift from the spectroscopic redshifts within the VO, for example. Redshift being the distance, essentially. And now we have our candidates. So here we have now selected the blue dots at the top, which are over-luminous compact sources that are matched to dwarf galaxies. So we started with just tables, and now we have we've gone a long way, essentially. And so these, the blue dots are similar, and then we have just 2 fast radio bursts that we've talked about before that are similarly located on this plot. So that's a good sign so far. Now we can look whether there's any information about the spectrum on some of these galaxies to see if the ionization fraction is coming from a star formation or a black hole, because we're looking for star formation in our case. So it went quickly, but the points were looking good so far. And now we can look at images. So now I'm just going to look, because we know the positions of these sources, we can download the images from the Astron Virtual Observatory Services to get the images. I'm going to do the same for an optical survey called PanSTARRS in the USA. So now we're just downloading images from these locations. And then we can merge these images together. So here I'm just combining these images on top of each other, essentially. So now we're going to see radio contours from the LOFAR survey on top of optical images in red, which are going to be the galaxies in the optical, and see where they fall. So whether or not they are at the center of the galaxy or a bit offset, like we saw earlier. And voila, now we have 16 candidates coming that might be interesting candidates to follow up for FRBs and further on imaging, for example. And now that we've run all of our pipeline, we can store all of that back into the data lake. So now using Ruscio, we can then push our results onto Ruscio like this. And then it's going to be stored for us to revisit later or to share with our collaborators that can then just log on to the platform and check what we've done without having to run the whole pipeline again. That's it. Thank you.
Okay. Thank you, Danny, for this impressive work on VRE, and also thanks again to the VRE team, because there is a lot of support from the team working with us and helping us in inserting all the work done in the VRE. So I have a few words to say about what's next. So you see that some projects are in a well-advanced status, others are still to work with the integration with the VRE. So we expect in the next 10 months to work with this full integration, to release the software in the ESCAPE catalog. And the important things that as Giovanni and the others say is that we create also tutorial documentation in order also for other students, other scientists that want to access to a different field of science to have an easy way to start, let's say, in this way. So this will strengthen and widen our collaboration among different areas, the different field of research. And we hope to insert this in the EOSC core and the EOSC exchange tool. So what are the open challenges? I think that we started many good projects. I expect that we go further. We plan to work more on the low latency and the real-time analysis. Most of the experiment will have the problem of the alert system. We can share the tool, we can share the solution, and we can work together on this using also a tool from artificial intelligence in order to really work together. And this will really help in consolidate and strengthen this collaboration. And I believe it is important that we work more on young scientists. So yes, more senior people has this duty. So we have to train the scientists, new scientists, with these diverse skills that comes from the physics, astrophysics, but also computer science, and also work in this infrastructure way with the common solution that the EOSC environment can offer us. So that said, we are open now to questions. So if some of you has a question for me, for the postdoc, for the Alessandro that is online, please go on. No question.
The same comment as before, although Katrina and yourself, you present this as part of the consolidation, I suppose that within also EOSC Future, there is the need, Ian, I suppose also for the reviews that are scheduled with the European Commission agency, that each single pilot has a sort of brief description of who is doing what, an abstract, and then what are the scientific goals and the open science added value. Then, of course, as we said, we have to envisage to translate all this in such a landing environment where the community can, where the colleagues can be acknowledged and the community can be onboarded.
Yeah, you're right. So we will work on this. We have a question from there.
Right, thanks. Raymond Ong from SURF again. This is very good work. Nice to see all of the stuff that does work. But my question is there anything missing or things that are not working as expected? What else would like to have, to do your work towards the future? And that's a question for all of you.
Yeah, it's thank you for the question. At the moment, I don't know if some of you that is working more directly on the integration have some answer, because I think that this is a good starting point. We will move forward. We are talking just during this meeting with the VR team. I don't know if each of you is already integrated the things in Rihanna, so we want to test more on, I'll say, EV computational things. So VRE is okay to show the notebooks, to show what we are doing, but if we want to move to production way of analyzing the data, we need to use different tools, but there are already, and we have still to integrate and check if it works for our fields. So at the moment we are in the good path. So the solution that were selected were good for us. I don't know if you have other.
If you agree, we can also. Sure, you agree.
I have to.
No, you don't have.
Based on discussions that we have together, I believe, and also with an outlook for what is going on with further open science projects, and trying to answer this question, I see three levels. One is the accessibility, the openness of the data that has to be discussed with the communities, with the research infrastructure, the different consortia. So there is a sort of communication that has to be put in place from you towards the community to which, on the RIs to which they do belong. There is another structural limit is the sustainability of all these things. And when you do open up to any single researcher, whatever is the request from the single researcher, where are the computing resources and who is going to provide them? So we come back to the classical question of the sustainability and the architecture model of EOSC that has to be taken. I know that there are working groups, but in my opinion, it's even more urgent today because we are, through EOSC Future, demonstrating that we have pilots and we are trying to change the paradigm. So we need to put in this in place. Now, the third, I don't remember anymore, but okay. I think, no, I think the third is to keep working, to keep the team, because all these tools, all these innovation approaches, since it is software, do you agree, Kai? Every 6 months you have something new on the market. So if you think that we have realized everything is completely wrong, although you can see that we have nice results, we have to keep the framework as scientific community alive and teaming up in order to really stay always at the front of the state of the art and implement whatever is coming from the scientific community, from the computing science.
I fully agree on this last comment, because especially in our field and the solution that we are adopting, something are already old. I'm talking more for machine learning solutions that 5 years ago are innovative, now are obsolete. So we have to move, and such kind of things have to be integrated in our software. Question?
Hi, I'm Anka Hienola. I'm co-coordinator of ESFRI Fair, and the co-visitor here. I have a question for you, the researchers. Did ESCAPE, through its tools and services, make your life easier? Research life easier? I'm not talking about the personal one. Probably not there. Would you recommend this? Do you see the added value of ESCAPE? And I want to hear from you. Thank you.
So,
it works.
Yeah?
Yes.
Okay. Well, there are some clear advantages to have access to a remote facility to do your compute. This means that you can, well, first of all, there's the sharing with your collaborators. So you can do it in one place and everyone can just log in and then see what's happening. So that's one great advantage, having such platform in place. Second is that then you don't, well, I guess you don't need to overload your personal machine to do your research as well. So then you can push all the heavyweight computing on some remote platform, and then your computer still runs fast. So that is a second advantage. It's a small advantage, but it's it's considerable. So did it make our life easier? It depends, I guess. So all of this was still in development while we were using it. And so this meant that there had to be quite a lot of exchanges between us and the team. But that's not a negative point, I think. I think that was also a constructive way such that some of our inputs can then become useful and can be put in place by a larger facility. Yes, I think overall it was quite constructive, I think. And having access to such platform means that over time, a bit as Kai Polsterer was mentioning yesterday, but this would also make a great platform for data scientists and students and so on to hop on and get the ball rolling quickly and not having to start everything from scratch every time, which often is the case when you're in research, actually.
Yeah, so about my experience, what I want to say, it's kind of a tricky thing because all this analysis was not starting from the scratch. So it means we transferred some analysis and deployed them inside VRE and using these tools. And I don't know how it would be if I would start with like absolutely ground-based level and start to develop my own analysis, but it's, probably it would be nice, I mean, and more powerful to use such services. But right now, I don't know.
Can you hear me? Yes. Yes, from my point of view, similarly, I approve all what Dani said previously. And we have to underline that we are not meant to be like the final users. We are the test case. So we went through the new process of trying to upload our own environment to the VRE in contact and collaboration with Enrique and Elena, Alba, and the team. But I can surely see the added value of accessing data simply, running a simple analysis on the VRE, on even using a web user interface as the Jupyter Hub, or reproducing an analysis with Rihanna. And I think that for the final user, as long as there is a good tutorial, a scheme for the user, it can be very, very good, especially for younger researchers, to run an analysis following principles for good software management even, and shifting away from the paradigm of being like, we can see this already in big collaborations of writing your own small R&D project by yourself, having to find the data, access the data, losing lots of time in the process. That's my opinion. So I surely see an added value.
Manon, you have a question. Can I just ask mine first? Oh, sorry, you had a question too.
Yeah, I can add. I mean, we're from the dark matter side of things, and today for us, no, it's more work, but we're developing the platform. We're learning how to use it. But for the person coming after me, absolutely. I got an email this morning from someone, oh, I'm going to use your code for run 3. What does this function do? How do I run it? And without this, you have to contact the person who did the analysis. But now the supervisor can just keep track of the links to the Rihanna and on the VRE, and here, this is how it was done. And I think that's absolutely crucial for the people coming after us.
Yeah, before we go to the question that I wanted to ask, it's not a provocative question, but a bit to all of us, and it's linked to one of the points that the head of unit from the European Commission gave yesterday on the stronger linkages with the university going forward in the work programme. And you mentioned before, Eleanor, how things have changed in the last 5 years regarding simply machine learning. Do you think that with the work you're doing and what you've described now, there is a consistent evolution also on the course curricula based on what's coming out now from the research point of view? So my question is, do you think the dialogue between university and research is completely updated so that the courses on offer are commensurate to what's being done in the innovative space of research and science? I don't know if that's a bit of an abstract question, but okay.
Maybe no, you want to comment before.
I guess I see it from the perspective of two universities. One is happily in the EU and the other is sadly not anymore. But in both cases, I think what we are doing also with ESCAPE has influenced the curriculum, because we are researchers and we're also teachers, we're also professors, we're also people that are influencing the curriculum. So in our kind of small, from bottom up, from really the researcher, we bring this connection, because what you're seeing here also, and both in the dark matter but also with Elena, we have undergraduate students working with us. So the first place where this makes a difference is in we have a bunch of projects, undergraduate projects, that expose students from universities to research. I mean, Axel is one of them, right? So that's one thing. But then there's also schools. There's a lot of research schools, and there's also research schools that are somehow across clusters. I mean, I know of one in London, for example, where people discuss how to do research, how to use tools, what are the best tools to use, so you have cross-contamination between different disciplines. And these are schools where they offer courses to all the students. So a student can come and say, I want 4 credits out of this research school. And I think this is a really great way to link what is done in ESCAPE. So these research schools, boot campuses, and this stronger connection will come also from us promoting it in the university. And the university have the ways to make this happen.
Yeah, I agree. I think that we are changing things. So ESCAPE and this kind of project offer the opportunity to bring innovative research solution also in university. So things are not so disconnected as this can appear, because when you are selecting also students, you are looking for this kind of skills. So in the future, this will happen more and more. That's why it is important, the training process for this young researcher, because this is what you are. We can find the best physics in the world that I can do, but at some point you need to have also other skill to go on with your research, and it is important we train. Also the young researcher, also master student researcher, this is happening. So it's not so far away in which this integration will happen more and more.
Just to add the comment that although indirectly linked to the training, the pedagogical offer of a university, the clusters had during these years initiatives in proposing training events, and in the specific case of the ESCAPE schools, we wanted to have the same partners and also the young or less young researchers among the scientific organizing committee of such training, in order to be sure that we were also responding with our offer to a need and a request. And this is a way also to shape and innovate the training offer.
Thank you. So Manon, do you want to pick up? You had something to say?
It was more of a technical question, so we're going back to the roots, sorry. But I was wondering about flexibility. What happens, for example, if you want to use the development version of one of the libraries? What happens if you want to use a library that is not pushed on the PIP registry or something like that? How do you do that? Is it easy? How? Yeah.
This is more for Enrique, the question.
Yeah, so if we are exploring those possibilities of how to do that, but for the moment, basically, the VRE allows you certain computing power to just do an exploratory analysis and just test things and before going to production, basically. Technically speaking, you just clean your repository and then run them locally.
Okay, thanks.
I don't think it works. Glenn, does it work? No, let's put that one down. Otherwise, people online can't hear.
We support the VRE team. So there is a team, Enrique spoke on behalf of Alba, Elena, so we have a team for the implementation, but also for the upgrading. So we do hope in the future to keep both approaches, a sort of VRE competent team between data scientists and physicists and scientists, researchers, in order to update the environment with other libraries. Furthermore, we have also in parallel the science projects that have to be hosted in, that for sure they will come with further requests.
Thanks.
Yeah, I think that now it's we are done.
Eleanor, thank you. And panelists, round of applause, please. And for our online panelists too, I don't know if he's still here. Alessandro, correct? Parisi. Right. Okay. So with that, we now go to the session just before lunch, and I'd like to pass the floor to the ESCAPE coordinator, Giovanni Lamanna. Thank you, Giovanni. Round of applause for Giovanni for putting all this together. Yes.
This is why we need the Silvana, you know. Okay. So what I'm going to do, make my conclusive talk, the title of which is the title of the conference, Escape to the Future. And as you probably understand, I'm going to give you elements that are part of the outlook for the future. So what's the starting point about this such outlook? Is the same figure from which we started yesterday through the introductory talk, that depicts the, is it an infrastructure? Anyhow, we call it the EOSC, our domain-based interpretation of the architecture of EOSC. It is based on bricks that you have understood, you have seen during the full presentations yesterday on work packages, but at the end, we attained the expected results. The work program is accomplished, and we can say that we have delivered, and we have now a running machine with all the elements which take care about the data infrastructure, the software catalogs, the different interfaces at the level of RI, at the level of community for user access. Saying that, we need still to make further step for the consolidation. I will come in a while, but I would like to take some part of the text of the review report, the second review report, where our external reviewers were encouraging us acknowledging a key role of ESCAPE in the construction of EOSC, thanks to this global consolidated view that we had. And they were really fostering, they were really recommending us to promote the strategic, conceptual, and unified vision of EOSC outside the ESCAPE community. Furthermore, they underlined that we should continue, as we have been doing now, to update and develop the services, and I would like also to add operate the services, according always to the user needs and, why not, the broader society. And I will try to interpret this recommendation in the next slides. Finally, in order to be amplifier of the voice of data producers and data curators, there are aspects that we have to take care about. We said the careers, we said the cross-fertilization, but also committing further in EOSC. So this inspires me, first of all, to repeat something that you have already seen yesterday, that the services that we have developed and we have deployed and that we want to operate are expected to be promoted, or at least some of them, into the EOSC exchange layer, and why not also for some of them in the core set of services. So the EOSC cell will not be a sort of island completely disconnected by EOSC. On the contrary, ESCAPE will commit into in feeding and into participating in the deployment of the final architecture of EOSC. But there is something more to mention. I repeat what I mentioned in the introductory talk, that it was extremely important, motivating the permanent discussions, and also that we have among the 5 science classes, discussions that became 1 year ago a sort of clear position statement shared among us about the expectation, the future, and the role that we should play in open science in Europe. And in this sense, we were also co-authors of a document which was addressed to the EOSC-Association. I suppose we will have time to also discuss the interconnection with the EOSC-Association later in the panel discussion. And this helped us to really pass the message of what are the priorities to continue having an important role in the open science, but to support further what we have been attending this morning, because this is just the beginning of the story. We need to support open science, and we are committing in that all together. What happened last 12 months, last year, is that the clusters through this document have also convened the different stakeholders or shareholders in a dedicated workshop, and we emphasized the importance of not only acknowledging the role currently for the future of the science cluster, really guaranteeing that the clusters could become platforms for open science and having a role in the Horizon Europe, because we were and this happened in all the domain, the 5 domain, we were combining, as we said also other times yesterday, the top-down approach. And I remember to all of you that top-down approach is because from the beginning, the call to which we address in H2020 the projects required the formal commitment of the ESFRI's project and landmarks partner in the classes. But most importantly, we see that the bottom-up approach, the community, the concerned scientists, the data scientists, computer science, that willing to work together and to pursue the cross-fertilization in science innovation was even more important. And by chance, we discussed really with the last questions raised to Ellen and Katerina the horizontal momentum is also important. The connection with the university institutes is not only simply being able to combine the pan-European dimension of the ESFRIs with the national dimension. Is really to play a role and to provide a contribution to the new academic and training schemes based on data research in the larger sense we can intend this. The 5 clusters together, and this obviously is also relevant for ESCAPE, has tried 1 year ago to establish a sort of timeline where you see that between this year and next year we are closing our H2020 project. We are continuing our engagement in EOSC Future, but we also define on a longer term a couple of stages where we have to run in parallel soon science cluster general objectives that, as we said many times, are related more to the consolidation of the data infrastructures, and then see more science cluster and inter-science cluster specific objectives up to the operational objectives. Now, the point is that everything is, from my point of view, is already the past, because we depicted our complete picture, our view for how we want to proceed, and I underline again the added value was the concertation and the complete sharing of the view among the 5 classes. So what will be the method? And here I'm happy to use this slot that I have of this talk to make the official formal announcement, although you already know, at least for the collaborators and colleagues in the current ESCAPE consortium, that the ESCAPE project moves to being an open collaboration. A collaboration agreement has been signed by the directors of the 9 ESFRI and other world-class projects, the logos of which are presented here. And this is really the consequence of the successful experience that we talked about. We have also a panel yesterday where distinguished members of the European Commission and of our domain have underlined the success and importance of keeping the momentum of the ESCAPE cluster. As it is mentioned here, we want to consolidate our action. We want to play our role in the open science in Europe, but also participating in the implementation of EOSC and the establishment of new sustainable cooperative schemes within Horizon Europe, the European strategy for data, and excellent science. Are we ambitious? I think yes, but we have all the room and the elements for updating our work program. And I will spend a few slides in showing in which sense we are going, at least based on the analysis that we can do by today. First of all, few comments about the new collaboration and the collaboration agreement. The collaboration will continue to work for a domain-based approach, particle physics and astrophysics together. It is already an important step that the 9 ESFRIs have signed, but by definition, the collaboration agreement is defined open because we do open up to further ARIs. We discussed yesterday also those ARIs that are new in the ESFRI roadmap, but also others that are willing to join the ESCAPE collaboration. The parties are considered, because we do consider the ARIs as producers and consumers of data, but at the same time, because those are big science projects, so we know that behind we have a huge international collaboration, not only European consortia. And furthermore, as it was the case in ESCAPE H2020, they will link with the most inclusive approach all the national institutes, all the researchers that are willing to participate. Potentially we can be global because our RIs are also international in many cases. As a last item, there was also a question about this, I remember was addressed to Federico Ferrini, is envisaging how open data science management infrastructure or whatever, something which is domain-based, but can play the role for all, for an economy of scale approach, and as well as for being more effective in order to extend uniformly to all the research infrastructure and the full community the architecture of EOSC, or the solutions that we apply or we develop for open data science. So what are the next challenges based on this evolution of our project? Now I'm bringing out from the co-signed by the 5 clusters position statement document some basic ingredients of the global approach. We want to have a 2 pillars approach, the pillar A for inter-cluster common data service co-development. And in summary, we said many times, we need to make the VRE completely operative if we want to support open science further. So there is consolidation work, but then we have also to work out in a very cooperative context, and we hope support within Horizon Europe, together with the other clusters, see what we can do for supporting inter-cluster projects for interoperability and commons. And then we need also, through this pillar as general objectives altogether, not only limited to us, to see what are the few core services that can be proposed into the EOSC series of services, and we need to find out some cross-border services, maybe to evaluate and validate through pilots. Since we said how the VRE is the word to summarize actually the support to open science, for the current work program that is again represented here for ESCAPE, this work program will continue. Each of the work package leaders have also demonstrated to all of you yesterday that they have clear steps further for consolidations and also for further innovation. So we have to keep this structure with this work program, and I hope that we have room and funding to support our work packages, because those participate to the services at the end for the virtual research environment for our community. But there is something more. The pillar B means delivering content to EOSC. The main contribution, according to our point of view, to EOSC until now, we said yesterday and we repeat again today, and we have a demonstration with the pilots TSP project within EOSC Future, is to give scientific content into the EOSC evolution path. Therefore, we want to commit as ESCAPE, and also I think I interpreted the message also from the other class, to manage open calls for disciplinary and multidisciplinary science projects, going farther than the current test science project. We have not to be limited for the current and future partnership. We have to be open to inter-RI contests. We have to be open to support scientists for smaller, even less structured communities with less experience. This is why I take in as a reference the question raised from you this morning. We need also to solve as soon as possible, or at least find the solution for the provision of computing resource for supporting in the best and most efficient way all the researchers that want to be onboarded into the VRE without any bottleneck. Because if we want to support an open science proposal, we have to be also able to host such a proposal. This is why I linked now to the VRE service work program also other programs. One block is the one of challenging open science objectives by RI commitments in open science projects, and as well as cross-cluster open science project. And now I'm trying to populating further the work program with other programs. But before saying that, there is an important question that will come on our shoulders, of the 5 classes, that we have to communicate. As you also said this morning, we need to really have a communication plan, and we have to also start to saying what an open science project is. In this sense, I try to make, I'm not going to details everything, but at least 4 natural ways of interpreting an open science in the case of ESCAPE. It can be a complete fair data scientific workflow that is developed and then made accessible within the ESCAPE VRE. It can be any development providing a service that strengthens the operation, widens the applicability of the ESCAPE EOSC cell infrastructure. Can be any cooperative action that aims at results extending the fair data stewardship to any new or emerging arise, or the individual researchers, as we said. And we should also add any of the above or further exploratory digital workflow that has the ambition to leverage fundamental science for society at large. And here, we come to the fact that we should be open and we should support cooperation with SMEs. We should support the use of the RI's data for innovation, technology, or cross-cluster projects that are not in our, how you used to say, the core business. We are not talking about fundamental research, but there are kind of data, housekeeping data, coming from our research infrastructure that are touching other disciplines. So those are also open science projects that have to be considered. We should really be open to any kind. And I'm sure that the other 4 science clusters have other interpretation of potential open science to add to this list. But this brings me to introduce the question of the sector data space. Just for your knowledge, we talk about the European strategy for data that aims at creating the market of data and subdivided in 9, if I count correctly, sectors. Through these actions, so these data spaces, there is the wish of the member states of the European Union to generate through data an impact for society and economy. I pick up this slide, I stay on the context. This was one slide that I prepared recently, participating to a panel discussion organized by the EOSC-Association, where we discovered, unfortunately I was not aware about, we talk about EOSC Exchange, I learned from here about EOSC Core, we have also EOSC Data Federation. Now, concerning data space, one thing that I wanted to say is, as you see in yellow, as you see also in the web page of the EOSC-Association, the Council of the European Union recognizes EOSC as the science, research, and innovation data space. So we are concerned by data space. We are concerned by the European strategy for data. Then there was a question about how do you see the EOSC Data Federation? In a few words, do you see that the EOSC should be the data infrastructure of something different? My personal suggestion that I want to share also with you is that we cannot neglect that are in place already at different level of maturity in different countries platforms for public access to scientific data. And with the intent clearly established of preserving sovereignty and multilingualism. I believe that the science cluster have a role to play in the EOSC Data Federation to propose domain-based data platform. And for us, it's really simple to mention this because we work in such a way. Data are coming from the big science projects, and they have the role of producing, curating, guaranteeing the accessibility of such data. But now, this brings me to tell you something more, that although you can think at the first sight that we are far away from all the different sectors, I'm proposing you examples of how our physics projects are concerned or have potentially a contribution to provide with their own data in different sectors. It could be with our capacity of R&D project, of innovation to participate to Industry 4.0. It can be about aligning our programs to match the expectations of our countries of the European Union in terms of Green Deal and energy. It can be also about federating the know-how or the needs of creating this know-how of different research infrastructures in partnering in ESCAPE of a common rules for airrise management or policy for socioeconomic impact model for the big science projects. Without mentioning, it is easier for me, again, the skills, the training, university, and the health data with the participation, obviously, of nuclear and particle physics facilities to the healthcare. Now, this helps me to let appear one second block, one more program, the synergies on sectoral data space. I go further, aligning further ESCAPE domain-based data to EOSC. I think that I don't have to say too much about that. We learned that there is already the Wi-Fi project. There are other projects that are wondering about the fairness of data and the open science services applied not only to offline data analysis, but also to the low latency data, the usage of edge computing, and so on and so forth. R&D technology data of our projects, in particular during their feasibility studies, their design study, generate data that are not data that the detector or the telescope are going to produce when running, but a lot of data that can be useful and should be accessible. And then technological, industrial, applicative, fair data platforms, again, those are the fair data platforms for data that are coming from our facilities, but they are used for clear applications in different sectors, and in particular for society and innovation. So this is why I think it is important to keep also a program that we can call ESCAPE Tech for concerning this low latency, close to the center, sensors, technology development, and the fairness applicable also to these data. Then I come to one more topics that was discussed again yesterday. We said yesterday also during the panel discussion that the European Council has reached the signatures of the countries about the evolution on the research assessment and implementation of open science. We learned by Leah yesterday that there is a group, a European-wise group, that is going to work on such an assessment. I took from the document signed by the governments four elements. The first one is concerns the fact that the scientific results should be in the future not limited to the publications, but all the digital objects behind them has to go with the publication. And we have also to recognize, therefore, in line with the FAIR principles, the work done by researchers in that. you realize immediately, this is for each sentence or more or less, I put a consideration that I want to share with you. You see immediately that the ESCAPE framework or even the VRE, or as I said before, we can talk about outreach when we say the landing page on the web, but in reality, we try to build the environment where we can find all these digital objects and we participate to the new research assessment and the assessment of the career of researchers. There is the question of taking into account the different implications in the history, in the career of researchers, but also the different implications, and we have a lot of different implications in the consortia that are supporting the construction and the exploitation of our RIs. We need to leverage the cross-domain competencies, and again, the promotion of careers demands the operation of VRE to access outputs behind the publication data, also in this case. We need also to, through the ESCAPE collaboration, organizing with discussions and an action with all the RIs to make a sort of list of different profile, different duties that are guaranteed by researchers that try to promote and to talk about the diversity of the implication of researchers in these projects. And then the final consideration is that this European group is going to try to propose figures or elements to assess the research. I believe that in our university, in our institutes, the evaluation, I know that the evaluation is based on peer reviewers. So it is important that our colleagues that are in committing to review our own careers are also ready to apply the new procedures for assessment. Therefore, we are at the first line to participate in educating ourselves and participating in proposing rules and figure of merits for the new assessments or for the new procedures. This is why I felt like important that in ESCAPE we consider the career developments as one more program that is totally, as you have seen yesterday during the panel discussion, that is totally linked with the ERA action, and the clusters have to consider this and ESCAPE as well. Apart from the cluster, I'm almost finished. Apart from the programs that we have added in the work program, we have to consider somehow instances. There is a clear expectation on Horizon Europe to leverage, to support further the competencies that we have put in place in our classes or existing competence centers. I believe that although we have to preserve the original mission and to keep the main focus, indeed we need to build an instance of competence center that is going to be a sort of reference for some excellence that we have in terms of data stewardship, in terms of data management, but also participate physically to be a sort of representative body of ESCAPE in the governance, in the evolution of the governance framework and the global architecture of EOSC. This is why we are proposing also to have an instance, ESCAPE CC, the community-based competence center for EOSC alignment, train and support, extended outreach, financial model for services, and to tackle all the issues that are still open that we have discussed today. I conclude with a second instance that is part of our work program in the new collaboration of ESCAPE that has also found the agreement and the interest and the participation very soon of the other classes, looking forward to build a sort of European Virtual Institute for Research Software. We said, Kai Graf mentioned yesterday that even in the first communication, in the first debates of EOSC, software was completely excluded. And we were at the first line mentioning that software is part of the digital objects. We have put in place innovation action, training, and we have put a lot of work to transform what was a repository in the catalog and even further with the VRE. Software will be important. I think you all share with all the talks that you have attended about software, and we want to build this. This is why what the European Virtual Institute for Research Software is going to be. Is going to be developed in collaboration across the science cluster and existing national competence centers, because in this context we do have such competence centers. Providing a framework to train and cross-fertilize knowledge between different science domains, a scalable approach to the stewardship of the scientific software for open science. The activity should build on work in national projects as well as international cooperative frameworks. We mentioned during the discussions yesterday that we have wonderful, excellent examples of foundation approach like the high energy physics one, and limited with the size of our project in ESCAPE, we triggered, we started up this innovation foundational group that was potentially transversal between particle physics and astrophysics. We want to plug further with the HEP Software Foundation. We want to go in this direction. And it will be part of the ESCAPE instance, Virtual Institute for Research Software, the raising also of the awareness of software and computing as a key enabler in science, and also the ensuring that the software development and scientific computing is regarded as a first-class activity of performing science. I think that this is important for many of the young researchers that you have that are dedicating a lot of time, a lot of efforts in software, and are really great in developing the software. So that's the global picture that for the time being we can present as a sort of updating of the new ESCAPE collaboration work program. Again, it is based on the core work program, and we update it with something which is already extremely aligned with the priority of the era, with actions that are already going to be taken in Horizon Europe, but will be also part, frankly speaking, of the common among the 5 science cluster influence action to have in Horizon Europe a further occasion to support such a program. So I concluded my outline with all the presentations. I presented to you the starting point, the method, and the list of main challenges that are tackled by such a work program updated. And since I don't have any more time, I conclude with this slide that I let you read. For us, open data and open research for ESCAPE is a change, but also a source of challenging opportunities. And please allow me to say once again, as I said in the introductory talk, it was really a fantastic, and it will be still a fantastic human adventure, because it enables expectations, commitment, cooperation, and inclusiveness. And we are really enthusiastic for that. Thanks a lot for attending.
Thank you, Giovanni. Great, very interesting. So the Research Software Institute, nice. I just wanted to point out we have René Book from the EOSC-Association CTO. They're lovely to have joined us. And I think maybe from the tail end of those discussions, René, we can bring also something in to the next clearly discussion that you're going to be a part of, which will be on the science clusters at 1:30, which is super as a nice concluding effort to the ESCAPE conference. We do have lunch now in the same place as we had before, but you won't be able to eat unless we have a photo, okay? So you're going to go into the room outside with all the dinosaurs. Ruben, you know, is there with a camera in his hand, so follow him. We'll get the nice photo, Giovanni at the front, obviously, and then you can eat.
Can I say don't miss the panel discussion, because we have our fantastic guest answering all your questions and also discussing with us. So after lunch, come back.
Yeah, please don't leave. Thank you. And thank you to our online participants that we had over 30 today. Thank you very much. You can leave your stuff here. Thank you.
De la base, de la base, de la base, de la base.